Bell Labs is currently engaged in research towards the development of an autonomous dexterous robotic hand. As a research tool, the Utah-MIT Dexterous Hand, developed at the University of Utah's Center for Engineering Design, provides a versatile and reliable vehicle for this research. The Utah-MIT Hand has 4 fingers, each with 4 independently controlled joints. Each joint is actuated by 2 tendons, one for extension and one for flexion. The tendons are routed away from the hand on a passive remotizer, allowing free rotation of the hand without unnecessarily stressing the tendons. Each tendon is driven by one of 32 pneumatic actuators in the actuator pack. Each actuator is separately controllable by an analog signal, allowing precise control of the positions and forces of the joints. To control the hand, a multiprocessing computer system has been developed. The system consists of component boards residing on a standard VME backplane. This card cage is an extension of the address space of a Sun workstation. A bus repeater connects the external cage to the Sun's VME bus. Software development, therefore, can be carried out on the Sun using the tools available through Unix. Programs can then be downloaded to processors on the external bus for multiprocessor control of the hand. Control signals to the hand are generated by 4 digital to analog converters, providing a total of 64 control outputs. Signals from the hand, which include position, velocity, and force information, are received by 2 analog to digital converters, providing 64 total inputs. Processing is provided by multiple 68020 processors, each with its own RAM memory and resident control program. In the current processing hierarchy, one processor acts as the master, controlling I/O to and from the Sun. It performs path planning and human interface functions. A second processor is dedicated to the execution of servo control algorithms. All 16 joints of the hand are controlled by this processor at a rate of approximately 250 Hz. All outputs to and all inputs from the hand are routed through this processor. A third 68020 is dedicated to tactile data processing. It addresses and reads data from tactile sensors mounted on the hand. It then processes and stores the data in shared RAM for other processors to use. The fourth and final processor is highest in the control hierarchy. It acts to manage, build, and inspect environmental and object models. The state of the hand and its relationship with the environment are processed here and made available to other processors for control of the hand. The primary control routine for the hand is a position control algorithm. A trajectory, either in joint or Cartesian space, is specified and the servo processor controls about the path. During motion, the compliance and damping of each joint or of the fingertip in Cartesian space can be controlled. This allows the specification of variable resistance to position disturbances and can be used to control forces exerted during the execution of motion. Manipulative actions are built around a set of simple motion primitives. Those shown here include pinching and rotation and translation about all 3 coordinate axes. The primitives are stored in the local memory of the servo processor, allowing the master to initiate a motion program by name, then return to another task while it is executed. The primitives are defined as relative motions of the joints. This allows them to be executed from any pose of the hand with equal validity. They can be combined by simple arithmetic operations, such as addition or subtraction, to build more complex hybrid motions. As shown here, a withdrawal and a rotation are combined to produce a screwing motion. When objects are within the grasp, the primitives can be executed in series to provide sequenced manipulative motion. Control with variable compliance allows various objects to be manipulated with the same sequence of primitives.